OK, let's get started. We're here today to test your memory, or well, maybe more likely, your knowledge of memory. I'm Dan, a product manager, and this is Ale, a software engineer, both working on the Google Play console. When we talk about app performance, we often think about the things that we can see, a buttery smooth 120 Hz UI, or an app that launches before your thumb leaves the screen. But these visible metrics are built on a silent foundation, memory. Performance as a feature affects both user engagement and your app's user retention based on responsiveness, stability, and battery impact. Until recently, we've been able to take for granted that devices would launch with more RAM than we had in the past. This is no longer the case. We see more and more headlines about companies who are having to make very hard decisions about whether to launch with the same, smaller RAM, increase the device prices. There's a wide range of industry constraints affecting this, but for us as app developers, it means we need to really think long and hard about our app's performance, how we optimize for memory, how we become good citizens of the memory that we are using. Optimizing your memory footprint gives you the best experience you possibly can for your users across the entire set of form factors that we have. We're introducing a clear framework of platform accountability. We want to recognize and reward excellent resource stewardship, while also protecting the overall user experience for the users of all of your apps and games. To do this, we're establishing clear, enforceable boundaries for apps that compromise system stability. As app developers, we have to transition from reactive troubleshooting to proactive memory budgeting. This means we have to change our practices, thinking about actively reducing memory overhead, catching leaks before they reach production, and keeping your app footprints completely lean by default. Across Google, to support you in this, we're investing significantly in our diagnostic toolkit. We want to bring deep, actionable memory telemetry directly from production devices in the field so that you can understand and optimize your memory consumption. OK, today we're going to talk about 5 things. First, we'll walk you through some foundational memory concepts and how they apply to Android, so we all have a very good foundational base. Second, we'll share new features that are launching on Play Console, some literally rolling out right now, to help you track your app's memory usage. Third, we'll dive into why R8 is so important and makes such a big difference to your memory footprint. Fourth, we'll talk about what you can do regarding bitmaps, how you can optimize them, reducing your memory in this way. And finally, we'll end with a couple of words on how to make your user experience more robust in case of system memory pressure. Sometimes these things are out of our control, and the app needs to be able to respond and come back to life in a way that the user would expect. Great. Let's dive in. Over to you, Ali.
Thank you very much, Dan. So I bet all of you care about user experience, and you spend weeks, months optimizing for perfect scroll, for no crashes in your app, but then you release it to your users, and they come to you telling you that the app might be crashed, might get killed by the OS, and you're wondering why. And usually, we can pinpoint problems down to one single concept, which is the one of memory. And to be able to really understand why, we need to go back to the basics of memory management on Android. And before we really dive in, I want to see here, the audience, how many of you already know about memory pages? OK, we have a couple of people in here. How many of you know about RSS metrics, RSS anon, RSS file? Not many of you. Then let me go into this. I'll spend 2 or 3 minutes just bringing everyone up to speed with the jargon so that all the later sections are way more meaningful. So first of all, let's start from memory. Here we have Android. Android's memory. Android does not look at the memory as a single stream of data, but rather it splits it up into small blocks that are called memory pages. Now, memory pages are being then managed independently by the OS, which can allocate them and evict them. And they are tracked through a couple of metrics, RSS file and RSS anon. Now, RSS stands for resident set size. That's the total amount of physical RAM that your app is currently occupying. First of all, RSS file. RSS file is for file-backed pages. So file-backed pages means pages that have a clone on the file system on disk. So these start in a state that is called like clean. So they have an exact identical copy on disk. And these are easy for the kernel to evict because they can just be brought back from disk when needed. Now, though, if you go ahead and change some of the content in these pages, for example, you go and write a user preference in a database file, well, this page becomes dirty. It cannot be evicted as easily as before. What the kernel needs to do is it needs to write this back into the file system, and then it can evict that. Moving on to RSS anon, which is for anonymous pages instead. Anonymous pages are all other types of pages, so any pages that do not have a corresponding content on disk. Think of things like any allocation of objects from your Kotlin code. And anonymous pages, similar to dirty fileback pages, the kernel cannot evict them very easily. What it can do, if it becomes under memory pressure, it can compress them and move them into ZRAM. ZRAM is the swap space on Android is a partition in the RAM that is used exactly for this purpose to copy over some inactive pages. And anonymous pages are essentially up to your app to manage. And what does this look like from a user perspective? So if the working set size, meaning the amount of the minimal amount of physical RAM that your app needs to operate right now, is getting closer to some limits that the OS has set, well, the OS has to act very quickly and has to do something about it to evict some of these pages. What it can do is it can attack file-backed pages. It can do write back and then clear up some of these pages. What happens in that case is that your app might need to wait for some I/O to happen in the background, so that can cause eventually some ANRs. On the other hand, it can instead attack anonymous pages. And in this case, again, it needs to compress these pages and move them over into ZRAM. But if it starts thrashing, meaning if it starts moving them back and forth between ZRAM and the anon pages, well, you will end up with a UI that stutters with some UI jank. Now, these part, the anonymous pages, are the ones that are the hardest to really evict, because that's data that cannot be pushed down on disk eventually. So we should dig a little bit deeper to understand where these pages really are coming from. So one place that they can come from is the Java heap. Now, the Java heap, you're probably familiar with that, is the piece of memory that the Android runtime manages. So the Android runtime data that gets allocated, any objects that you create in your app, end up here in the Java heap. If the Java heap is growing too large, then what the Android runtime does is it will throw an out-of-memory exception. And even if you try to get a bit more space, for example, by using some flags in your manifest, like large heap, well, it's not really free lunch. At some point, you will hit some physical limits, and you will get this exception thrown. On the other hand, we have the native heap, which is where anything like your native library allocations, any database files, any software bitmaps will actually live. And this is essentially invisible to the Android runtime. The Android runtime will never throw an out-of-memory exception if this space grows. So historically, this has been the area of memory that has caused most unbounded growth, and just because it cannot be policed by the Android runtime. This has changed in Android 17. So Android 17 introduces a mechanism that is based on Linux C groups to essentially create a hard boundary around your process memory, so that no matter whether it is anonymous pages or whether the anonymous pages are coming from the Java heap or the native heap, they will all account for your memory budget. So just in other words, your RSS anon and your swap all together get compared to some thresholds, and the system might decide then to take action if this is growing too big. So this is all the theory. Now, hopefully, that we have all our common jargon. And now Dan will talk to you about how you can actually monitor all this. Over to you, Dan.
Fantastic. Thanks, Ali. To make it easier for you to keep an eye on this metric and more, we're up-leveling Android Vitals in Play Console to give you the insights you need so that you can understand your usage directly from the field. Let's start with something completely new. This is literally rolling out now. Started at 10% this morning, and so it might be at 100%. I don't have my phone, so I don't know the exact latest status. But we're adding a new memory section to Android Vitals. To start, you'll see this memory usage metric composed of anonymous, RSS, and swap, as Ali just introduced. This is your dirty memory usage. This metric is a little different from any other Android Vitals we've had in the past. We have percentiles for the first time, e.g. you'll see P50 and P90. Two percentiles that are particularly important, P99 and P50. Memory leaks will typically appear as a very high P99 and a much lower P50. So this can be one way to do some initial troubleshooting. We have the whole gambit of other percentiles available here to help paint a fuller picture for you. We have regular breakdowns, but we've also included a filter for app states. Apps don't just live in the foreground. They live in the foreground, foreground service, background, and cached. Memory usage varies differently across all of these states, so you can use this to kind of drill down and see what happens in different states. A histogram will help you to visualize the overall distribution, and you'll be able to drill down into individual RAM buckets, where we have histograms available here too, so you can see how you perform on lower-end, medium-end, and high-end devices. OK, great. Let's say with one of these RAM buckets, you identify high memory usage, and you want to use R8 to improve it. How do you know how well optimized your app is when it comes to R8? If you have direct access to your build tools, you can use some of the tools that Ataul is about to introduce. But if not, what can you do? We're integrating R8 analysis signals directly into Play Console's App Bundle Explorer, so that's just a few clicks to see some of the detailed information here. In the next roughly week or so, you'll start to see if you're using R8 or another optimizer, how you perform across 3 key metrics, and finally, any issues that you might have with your configuration. You'll have to use R8 with AGP version 8.8 or above to see this. So if you see limited data, you'll need to upgrade yours. I heard in a previous talk there's a skill available, so definitely use that. And side effects of upgrading also include stronger optimizations, so it's a win-win. Finally, we'll also launch recommendations on the Android Vitals page, so you can see if you can squeeze anything further out of your R8 configuration. OK, let's rewind slightly to I/O itself. We've launched enhanced crash reporting, so you can now filter for out-of-memory crashes. Today, we don't see too many of these, but as memory pressure increases, you might start to see more of these for some of your sessions. You can get to this under crashes and ANRs in the navigation, under the filter, insights and potential fixes, and then just select this new option here. And finally, for those not yet making the most out of the Android app bundle, we've launched some recommendations and insights if you haven't enabled density splits. We'll cover more on density splits later, but the key takeaway for now is that they enable app stores to ship the most optimal assets for a given device. This reduces data transfer and, crucially, reduces the memory usage on those specific devices. OK, these high-level insights are great, but what if you want to go a level deeper? This is where the Profiling Manager comes in. Profiling Manager is an advanced performance API introduced in Android 15. It's the only API that lets you collect real user performance profiles programmatically. Since its launch, we've scaled up the number of event-based performance triggers significantly. These were introduced in Android 16, and we've introduced 4 new in Android 17, starting with cold starts, excessive CPU kills, and 2 related to memory, out of memory and anomaly. We work with Datadog, a cloud-based observability and security platform, to integrate this API directly into their real user monitoring and continuous profiling platforms. The integration allows you to automatically capture low-overhead, code-level performance traces from production devices to instantly diagnose root causes from real devices in production. To learn more about their collaboration with us, take a picture of this, and you can check out the details later. Firebase Crashlytics is also exploring integrations with Profiling Manager to provide real-time automatic heap dump capture of memory-related terminations. It removes the need to build bespoke pipelines and allows you to tie metadata, like your logs, rollouts, keys, to those heap dumps so that you can diagnose more easily. If you're interested here, take a picture of this as well, and then you can check that out when you have a spare few moments. OK, that was quite a lot. But let me now introduce and hand over to Ataul, a developer relations engineer working on the Android team, to explain why R8 makes such a big difference to your app. Thank you.
Thanks, Dan. Hey, everyone. As Dan just mentioned, I work on the ADR team for Android. I'm going to spend the next 10 to 15 minutes talking about two of the most important areas that you can focus on when it comes to memory optimization, starting with R8. So when we talk about app memory, it's very easy to overlook our compiled code. But the reality is simple. Every class, method, lambda, and string constant has to sit inside RAM when it's executed. And that's precisely why R8 makes such a big difference to your app's memory footprint. When your app launches, the kernel maps your DEX files and native libraries into virtual memory, delaying the use of physical RAM. When your app references or calls a method or a class, the CPU looks for that in physical memory, and it's not there. And this causes a page fault. When that happens, the kernel pulls a standard 4-kilobyte chunk of your DEX file from storage into physical RAM, linking that code in virtual memory, and then the CPU can retry and access it. And now that it's in RAM, the Android runtime creates descriptors for everything declared in that class, storing all of that information as anonymous pages. But what if it was a large class, one that's spilled across multiple 4-kilobyte chunks of DEX code? Well, it means multiple page faults. Art's class linker will follow references to other classes, loading those as well. And it quickly becomes a huge spider's web. These classes need to be loaded in memory just because they're referenced. The descriptors end up being stuck in RAM for the entire remaining lifespan of your app's process. Tools like R8 are therefore completely non-negotiable. Dan mentioned there's new integrations in Google Play Console, which highlight findings and recommendations for code shrinking and optimizations. We can look at Monzo, a UK and now European bank, as a real-world example. Monzo's Maria was blown away by the impact that R8 had. They enabled full R8 optimizations, dropping their ANR rate by 35%, improving cold startups by 30%, and shaving 9% off their total app size. But enabling R8 isn't enough. If you want to see results like Maria, you need to make sure that you've got the right configuration. And for that, we've got the R8 configuration analyzer. This launched earlier this year, and it plugs directly into your build pipeline, analyzes the final merged configuration for your app, and outputs 3 concrete metrics. The shrinking score is the exact percentage of your classes, fields, and methods that are open to dead code shrinking. The more that R8 can remove here, the smaller your DEX file gets, and the less memory is required for your code. The optimization score is the percentage of your code base that's available for structural optimizations, like method inlining or class merging. When R8 inlines a method, it's literally copying the body of the method directly into the call site. So by eliminating the separate method reference, you reduce the structural complexity of the class layout. Because the better that R8 is able to inline methods and classes and collapse the redundant entities, the smaller and tighter that your class layouts become. Finally, the obfuscation score measures how much of your code can be obfuscated, which is basically renaming classes, fields, and methods with short alternatives, which consumes less memory. My favorite part of the tool is the keep rule analysis table. What it does is it breaks down your program file line by line, calculating the precise percentage of optimization that each individual rule blocks. Here it's highlighting that the obfuscation score is 0%, and it's caused by a single rule: don't obfuscate. If we check the configuration, sure enough, there it is. 3 global rules that are preventing R8 from doing its job. So let's remove them all and rerun the analysis. And the scores leap up. Hooray. OK, so that wasn't a contrived example, but it does show clearly how the tool demonstrates the impact of each individual rule. It lets us also group analysis by file, which lets us see if a particular SDK is causing issues. Library developers are encouraged to package consumer rules files if they need to protect symbols accessed via reflection. Just like app developers, library developers should avoid using package-wide rules and instead be very specific so that R8 isn't blocked from removing unused library code from the app. Here, the author of the Balloons SDK, Jae-young, also known as Skydoves, made a really small change that impacted the demo app's R8 scores by 2% across the board. And while 2% might not seem like a big deal, you have to imagine how it would stack up based on how many libraries you depend on. I'm very happy with the tool that the team have built, and I think you'll find it helpful as well. Use the R8 configuration analyzer so that you can fix low-hanging fruit in your own code base and also file issues with the SDK authors when you find that they're using overly broad rules. So Ali gave an introduction to memory, Dan showed us how to track memory metrics, and I just explained why R8 is so important. Before I hand it back over to Ali for the final section, I want to spend the next 5 to 10 minutes talking about one thing that I think that everyone in this room, well, all of our apps in this room have in common, which is bitmaps. In this section, we'll go through 4 tips when working with bitmaps, explaining not only the what, but the why. And the first one, load only what you need. It sounds obvious, but why? Say we want to display a remote image in a 150-dip image view. We'll use an image loader like Coil or Glide to write the file to disk first. Once it's safely on disk, the image loader prepares to decode it into a pixel array in memory. And it tries to protect our RAM by using Android's bitmap factory to downsample the image to avoid loading a large bitmap into a potentially small layout target. The way it does this is really important because you can help it perform better. Downsampling using Android's bitmap factory uses a field called inSampleSize. It tells the decoder to skip pixels during decompression, effectively dividing the output dimensions. So if the inSampleSize is set to 2, you get half the width and half the height, which means you only need to load 25% of the pixels. And it has to work out the shrink ratio, the difference between the source size and the target. The decoder uses bit shifting for speed, so it can only use powers of 2, which means that the system often has to round down, which does get us closer to the target, but it's not precise. So now we've got a decoded image in memory that's smaller, but it's not quite perfect. To bridge that gap and fit our exact 150-dip bounds, the image loader is forced to run a second fine scaling pass, during which there will be a temporary spike in your RSS anon. And that's because the image loader has to allocate a second, smaller target buffer to handle that scaling math. But after it's done, it can safely discard and recycle the original in-between allocation, though during that process, both bitmaps overlap on the native heap. Image loaders do make it quite easy to request the correctly sized image from your backend by providing the target's dimensions. Here, Coil uses the interceptor API to provide the dimensions in pixels, and then you can use that to request the exact image size you need. And similarly, Glide also lets you make requests based on the target view size. You first have to register a model loader factory, so you can pass in parameters like the width and height, and then return a URL with the dimensions of the target baked in. Ultimately, we want to use server-side sizing so that we don't have to load more in memory than we'll actually use. But if our goal is to optimize memory, which file format should we get from the backend? Actually, it doesn't make a difference. All the images are decoded into a raw, uncompressed bitmap. So the size is actually dependent on the bitmap config, which determines exactly how many bits of memory are allocated to store the color data for a single pixel. ARGB gives us perfect color fidelity and full transparency support, but it's the most expensive software option that we have. RGB 565 completely discards the alpha channel, but it's the perfect choice for small thumbnails in lists where the user won't recognize subtle color banding or small differences like that. If you can, default to using hardware bitmaps. So these live directly on the shared graphics buffer, which don't count towards your app's RSS anon metric. Can you tell the difference between these two thumbnails? Using the cheaper bitmap config could save you 50% of your RAM. So if you're currently using ARGB, try it with a lower fidelity option and see if you can notice any difference. Up until now, we've focused exclusively on loading remote images, but local assets are just as important. For icons, buttons, logos, and line art, forget PNGs or WebPs. Your go-to, as it has been for the last decade, should be vector drawables. Because a vector is stored as pure mathematical instructions, it stays crisp when it's rendered on a low or a high resolution device, all from the same file. For vector drawables, the size on screen dictates how much memory is used. So while the vector file itself on disk is the same size, the RAM footprint scales with its dimensions on screen. So a smaller physical size requires fewer pixels to rasterize. Therefore, a 48-bit image might only cost 80-ish kilobytes of memory, whereas a 360-bit image could cost 4.5 megabytes. With Compose, vector paths are drawn using hardware acceleration. So they live purely in graphics memory, and the moment it scrolls off screen, Compose instantly destroys the layer, preventing permanent memory waste. For all cases, then, the takeaway is simple. For small, clean geometric shapes like icons and logos, use vectors. And finally, when it comes to local bitmaps, we often jump straight to framework APIs like Painter Resource in Compose. These are really fast, but that speed does come at a cost. These APIs decode the images at the full resolution and then apply a software scale to match the target. It's an intentional system design decision designed to prioritize speed over memory. So if you use these APIs, make sure you provide images at different resolutions so that you don't waste RAM. If you don't need the instant resolutions that these framework APIs provide, then you don't have to use them. Instead, prefer using image loaders like Glide or Coil. These do perform the downsampling and maintain a cache so that recent images reload instantly. And those were my 4 quick tips for handling bitmaps. Number 1, load the appropriate size image for the target. Don't include padding in your bitmaps either. So if you need space around an image, use something like a Compose modifier to add that at runtime, and that way you don't have to load blank pixels in memory. Check whether your app looks fine decoding images with a cheaper config like RGB 565, because it could literally halve your memory footprint. Vector drawable should be your default go-to when it comes to loading small images for icons. And finally, if you're loading local assets, consider using your image loader as well to benefit from downsampling and caching. I'll hand it back over to Ali to present the final section on building app resilience.
Thank you, Ataul. So thanks, Ataul. We have been talking about, and we gave you a few tips on how to be a very good citizen on Android and to decrease the memory pressure that your app brings in. But this is a shared system, right? So sooner or later, there is going to be a moment where the OS decides to kill the process. So we are going to look into a couple of things on how to make your app reliable and resilient to crashes and the OS killing your process. First of all, let's talk about the low memory killer daemon. This is a background OS process that kicks in when the OS is under memory pressure and needs to start evicting pages. And it looks at processes and puts them along a scale that goes from a low number, which essentially means something really important that is very visible to the user and should be killed as little as possible, down to bigger numbers as we get more and more into the background. So you've got the system processes out there on your left. Then we've got foreground apps. We've got perceptible apps, so something that is not in the foreground, but is still somewhat visible to the user. And then we keep going down into further and further things into the background or cached apps. So when there is a memory pressure where the low memory killer daemon will start from the right, going to the left, starting killing processes, and ideally it will stop at something in the background, but if the memory pressure is really severe, it will have to start killing something more here to the left, and it might actually come after a foreground app. And that's what this metric here in Play Console actually tells you, is the user perceptible low memory kill. And essentially, that tells you how many times that your app has been killed by the low memory killer daemon while it was in the foreground. So it was actually a visible crash for the user. And you want that metric to be as close to 0 as possible, because if it's more than 0, then most likely it means there is a problem with your app. Most likely there is a memory leak somewhere, and it becomes really important then to track what's going on, track why you have been killed by the OS, so you can pinpoint the memory leak and fix it. How do you do that? How do you track why your app was killed? So one thing you can do is at App Startup, you can ask the activity manager to give you all the historical process exit reasons. So that is like the list of the last times your process has been killed, and it tells you both why it has been killed and what state your app was in when it was killed. So here I've simplified a tiny bit. I'm only comparing to importance perceptible, which means I'm only checking whether that could have been visible as a kill to the user or not. You can use many more, like you can get much more granularity if you compare to other constants that correspond to various levels of importance. And then the first thing I do here is I check the reason. If the reason is low memory, then it means that the low memory killer daemon has killed my app. So I will track, I will log the fact that it has been killed by the low memory killer daemon and whether it was visible or not. Another thing I want to do is, you remember I told you that in Android 17 we have introduced a new mechanism based on C groups to limit your anon plus swap memory. Well, that is also something that you can check here. You can look for a description which needs to contain memory limiter anon swap. Soon there will be a reason that you can look for as well. And this was just the big red button that the OS has to use if the memory pressure is extreme. There are also other mechanisms that you can use in your app to be more proactive in releasing resources as the system memory pressure builds up, so the OS does not have to get to as far as killing the app. The main thing that you can do here is the on-tree memory callback. So if you register the on-tree memory callback, that gives you also a value that indicates the severity of the memory pressure right now. And based on the level of memory pressure, you can decide whether to trim your cache or to completely remove the data that is in your cache. And if you look at like Glide or Coil, they will also do that automatically for you. So they might decide to either trim the cache or remove the content of the cache completely, depending on the severity of the current situation. But watch out for the defaults and always double check what these libraries do. Because, for example, if you look at Coil 3 has introduced a new API that lets you decide, lets you tune what is the maximum size of the cache that you want to keep when the app goes into the background. Now, the default is 1, so by default, it does nothing. It doesn't trim the cache. Now that you know that, you can go and you can try to actually set a value that is lower than 1 and tune this parameter. So let's try to bring it back to our goal. So we have tried to minimize our memory footprint by using arrays effectively. We have been very intentional in how we use bitmaps. And finally, we have been responding to some platform signals like on-tree memory. Now, this might still not be enough in some corner cases, so the OS might still decide to kill us. Now, my last couple of tips is about how do we actually bring our user back into the app as smoothly as possible if the OS has decided to actually kill the process. First thing that we want to do is make our app startup as smooth and as quick as possible. And the first thing is use arrayt? Well, we have already talked about arrayt at length. Ataul gave you a lot of tips. These all still apply also for app startup, because everything like code shrinking, obfuscation, method inlining, and all of those nice things that Ataul explained will make the DEX file smaller. So that means fewer page faults, fewer I/O operations. So that means faster startup. There are a couple of other things that we can do on top of just using arrayt. We can enable startup profiles. Startup profiles are a way for arrayt to reorganize all of the code that you have in the DEX by putting everything that is used at app startup closer to the beginning of the main DEX file. So that means, again, that there is less to load at app startup, so faster load time. Finally, baseline profiles. This is a mechanism for the Android runtime to learn about some hot paths in your code so that it can decide to compile it ahead of time, meaning like at app installation, rather than at app startup as like just-in-time compilation. So again, all of these things will make the startup of your app much faster. Finally, one last tip for you is remember to save state. Because if I'm your user and I'm there on your app, I might be scrolling through a scrollable list. I might be filling in a form. If the process gets killed and I haven't saved the state, well, when the OS reboots my app, well, my app will have lost all of the UI state that I was in. So what you need to do is use rememberSaveables in your composables and use a save state handle in your view models. So when the OS brings your app back, it won't be just landing on the page that the user was in, but it will be on the exact place where the user was with forms filled in. And with that, I think that is all the content. I will bring Dan back to stage for some final words.
Thank you, Ali. Today we covered a lot, starting with how Android uses physical RAM under the hood and new metrics launching in Play Console. We looked at steps you can take, like using R8, optimizing your bitmaps, and then how you can build resilience when these kills do ultimately happen. Let's be crystal clear. The focus on memory is no longer optional. You can expect a continuous rollout of new memory management features and platform APIs, new dashboards and metrics in Play, new guidance on developer.android.com, and stricter rules on acceptable memory usage. Thank you for joining us today.